Every time you use GPS, you're relying on Einstein's theory of relativity. Without it, your location could be wrong by several kilometers. But why does time itself have to change for GPS to work?
Hey everyone, and welcome to this explainer. Today, we're diving into something pretty wild. We're going to explore how the absolute, mind-bending physics of relativity is constantly working behind the scenes to save your smartphone's navigation from total chaos. You might think of Einstein's theories as something that only really matters in deep space or, inside giant particle accelerators. But the truth is, you're literally carrying the practical application of relativity around in your pocket every single day.
So why exactly does your GPS care about relativity? Well, let's dive right into it. Without the principles of relativity, your global positioning system, your GPS, would actually become completely useless within minutes. The whole system is essentially a giant, incredibly delicate clock. It relies on a hyper-precise synchronization of time between the satellites orbiting way up in space and the receiver sitting right there in your hand or in your car.
To put that into perspective, if we just ignored physics completely, like if we pretended relativity didn't exist, the navigational errors would pile up at a rate of more than 10 kilometers per day. Imagine trying to find a coffee shop and your map tells you it's literally in the next town over. Within just a few minutes of turning the system on, it would be entirely broken for everyday use.
And here's where things get tricky. Because those satellites are moving incredibly fast and orbiting high above Earth's gravity well, their onboard clocks experience a net gain of 38 microseconds every single day compared to the clocks we have down here on the ground. Now, I know what you're thinking. 38 microseconds, that sounds absolutely tiny, right? But to get that standard navigational accuracy of 5 meters, the system needs to know the satellite time to a razor-sharp accuracy of about 17 nanoseconds. So that 38 microsecond drift, it completely obliterates that requirement.
All right, moving on to Section 1, Einstein's Special Relativity. To really understand why these satellite clocks are so off, we have to break the problem into two distinct parts. First up is special relativity, where the core postulate is that the speed of light is constant for all observers, no matter what their inertial frame is. Because of this, if velocities get high enough, classical Newtonian physics just stops working. It has to be replaced. And one of the most famous consequences of this is that moving clocks actually run slower than stationary ones. It's a phenomenon we call time dilation.
Physicists love to illustrate this using a thought experiment called a light clock. Just imagine a clock that ticks every time a single photon of light bounces between two mirrors. When that clock is just sitting stationary right next to you, the light travels straight up and down. Simple enough. But when that same clock zooms past you to the right, from your perspective, that light has to travel on a longer diagonal path. And since the speed of light literally never changes, traveling that longer distance just has to take more time. The time interval between the ticks is physically stretched out.
Okay, bringing this back to your phone's navigation system, GPS satellites are zooming through space at a speed of about 3,874 meters per second relative to the center of the Earth. Because they're moving that fast, special relativistic time dilation kicks in, and it causes those satellite clocks to lose about 7 microseconds a day compared to clocks resting down here on the ground. From our perspective on Earth, their clocks are running in slow motion.
And this is exactly the principle that leads to crazy sci-fi scenarios like the famous twin paradox. If you take this concept to the absolute extreme, an astronaut traveling to the star Sirius at 99% the speed of light would experience time incredibly slowly relative to us. Over a round trip, that space-traveling twin would age only 2.3 years, while their twin waiting back at home on Earth would age 16 years. Space contraction and time dilation fundamentally alter their respective realities.
Let's look at Section 2. General Relativity and Gravity.
Now, speed is only half the GPS puzzle. We also have to account for the environment of space itself, specifically gravity. The whole conceptual foundation of general relativity relies on something called the equivalence principle. At its most basic level, it proposes that locally, the effects of gravity and the effects of acceleration are essentially exactly the same thing. You literally can't tell them apart.
Einstein realized this through a truly brilliant thought experiment. Imagine you're standing in a stationary elevator here on Earth, feeling the pull of gravity. Now imagine you're in an elevator in deep space being accelerated upwards at that exact same rate. Einstein realized that, locally, your physical experience in both elevators is completely identical. From that insight, he deduced that gravity isn't just a simple pulling force, it's actually curving the very fabric of space-time. And curved space-time means time itself flows differently depending on how deep you are in a gravitational field.
If you take this to the extreme, like near a rapidly rotating Kerr black hole, the curvature is so intense it causes something called frame dragging. Space-time itself physically swirls around the black hole, kind of like water spiraling down a drain. Now, thankfully, we don't have to worry about black holes near Earth, but even Earth's relatively weak gravitational well causes a very measurable shift in how time flows.
General relativity tells us that clocks sitting deep down in a gravitational well, like us on the surface of the Earth, run slower than clocks out in weaker gravity. Because our GPS satellites are sitting way out there, orbiting at an altitude of over 20,000 kilometers, they experience much weaker gravity. And because of that, their clocks tick faster than ours, gaining 45 microseconds a day.
So, here is the ultimate math problem that actually makes your Maps app work. We combine the 7 microsecond loss from the satellite's sheer orbital speed with the 45 microsecond gain from experiencing weaker gravity, and we get our net 38 microsecond daily offset. So how in the world do engineers fix this? Well, they intentionally break the clocks. They tune the satellite's atomic clocks down to exactly 10.2299999543 megahertz before they even launch them. They purposely make the clock run slow on Earth so that the sheer, unavoidable forces of relativity fix it once it gets up into space. How cool is that?
Moving on to Section 3, Proof from Cosmic Muons.
Now, you might be thinking this is all just theoretical astrophysics and high-end satellite engineering, right? Well, not quite. We can actually catch relativity in the act right down here on Earth's surface. High up in the atmosphere, energetic cosmic rays are constantly smashing into molecules, creating these unstable elementary particles called muons. These muons then rain down toward Earth at incredibly high speeds. And university students actually run lab experiments using scintillation detectors to measure them. The detector flashes when a muon enters and flashes again when it decays, allowing us to precisely measure their lifespans.
Here's the mind-blowing part. Experiments show these particles have a mean lifetime of just 2.14 microseconds. That is incredibly, vanishingly brief. In fact, mathematically, even traveling near the speed of light, these muons should decay long before they ever reach the ground. But they do reach the ground, in massive numbers. Why? Well, because from our perspective on Earth, their immense speed means time dilation is actually stretching their lives out, letting them survive the journey. It is literal relativity in action, hitting the Earth's surface every single second.
Which brings us to Section 4, Debating the Lorentz Transformations.
So time dilation is definitely real, right? Our GPS works, our muon detectors flash. But the exact mathematical framework describing the underlying reality of this is actually still a subject of fascinating debate in the physics community. There's an interesting theoretical clash over the space-time transformations used to calculate these effects. On one side, you have the standard Lorentz transformation, which argues that space and time are inextricably mixed into a single space-time, making measurements subjective. But on the other side, there's an alternative framework called the GPS-LT. This one actually aligns more closely with classical Newtonian physics, arguing that space and time are completely separate objective entities.
Let me explain. The standard Lorentz transformation suggests a perfect symmetry. It dictates that it is always the moving clock relative to the observer that runs slower. So imagine two ships passing each other in space. Pilot A thinks Pilot B's clock is running slow, but Pilot B is certain that Pilot A's clock is running slow. Measurement becomes entirely a matter of subjective perspective. But mathematically, some physicists argue this creates huge paradoxes, because you have two observers who fundamentally disagree on basic, simultaneous events. But then there's this alternative GPS-LT framework which aims to resolve this contradiction. The math here argues that elapsed times between reference frames are strictly and directly proportional by a unique constant. Basically, this means that, at least in principle, we can objectively know which clock is actually running slower. It maintains an absolute, universal standard for simultaneous events, all without having to mix space and time together.
Which brings us to a really fascinating question to wrap up on. If this alternate GPS-LT model successfully accommodates our daily satellite corrections, the exact same corrections that keep your smartphone's navigation perfectly accurate, and it does so without mixing space and time, does that mean Isaac Newton's classical 17th century view of absolute space and absolute time was actually partially right all along? It really just goes to show. The universe is full of mysteries, and the mundane tools we use just to navigate to the grocery store are deeply tied to the foundational fabrics of reality itself. Thanks for joining me for this explainer. Keep wondering, and we'll catch you next time.
So the next time you open your GPS, remember, you're not just using satellites. You're using Einstein's universe. But here's the real question. If time can change with speed and gravity, what does that mean for the future of space travel? Let me know your theory in the comments. What do you think? Can time really change? Subscribe for more mind-bending science.